Specific heat capacity. If a certain amount of heat, delta Q, supplied to a system results in a change in temperature of the system from T to T plus delta T, then the heat capacity of the substance is S equals delta Q by delta T. The heat capacity S is proportional to the mass of the substance present, but may be different for different materials. In order to define a material-specific constant, we divide S by the mass of the substance M to get S equals S by M equals 1 by M into delta Q by delta T. The term S is known as the specific heat capacity of the substance. The value of S depends on the nature of the substance and the temperature at which it is at. Its unit is joule per kilogram per Kelvin. Instead of defining the amount of the substance in terms of mass, we may define it in terms of moles mu. The specific heat capacity per mole is then defined as C equals S by mu equals 1 by mu into delta Q by delta T. C is known as the molar specific heat capacity of the substance, and like S, depends on the nature of the substance and its temperature, while being independent of the mass of the substance. The unit of C is joule per mole per Kelvin. The table here lists the measured specific and molar heat capacities of solids at atmospheric pressure and at ordinary room temperature. We can use the law of equipartition of energy. We would learn about it in the next chapter. That is used to determine specific heats of gases to predict molar specific heat capacities of solids. Let us consider a solid with n atoms. Each atom vibrates about its mean position. The average energy of an oscillator in one dimension is 2 into half kBt equals kBt. So in 3 dimensions, the average energy is 3 kBt. Therefore, for a mole of solid, total energy is U equals 3 kBt into Na equals 3 RT. At constant pressure, delta Q equals delta U equals P delta V equivalent to delta U. Here, delta V is negligible. Therefore, C equals delta Q by delta T equals delta U by delta T equals 3R. From the table, we can observe that experimentally measured values are true to the above equation at ordinary temperature. Here, carbon is an exception. At low temperatures, it usually does not work. While measuring the specific heat of water, precise observations showed that its value varied slightly with temperature. The plot for this variation is shown here. Before the SI unit system came to be adopted, heat had the unit calorie. 1 calorie or 1 cal was the heat required to raise the temperature of 1 gram of water by 1 degree Celsius. However, since the specific heat of water varied with temperature, it was necessary to specify the temperature at which this heat transfer took place, which was 14.5 degrees C to 15.5 degrees C. With the advent of the SI unit system, the unit for energy, joule, began to be used for heat instead of the calorie. The specific heat capacity of water in SI units is 4,186 joules per kilogram per Kelvin, or 4.186 joules per gram per Kelvin, which would be the SI unit for 1 calorie. We noted earlier how the specific heat capacity was dependent on the path taken by the system to get to its final state. For gases, we may define 2 specific heats: specific heat capacity at constant volume and specific heat capacity at constant pressure. For an ideal gas, we have Cp and Cv. Here are the molar specific heat capacities of the gas, while R is the universal gas constant. To prove this, let us begin with the relation delta Q equals delta U plus P delta V. If delta Q amount of heat is absorbed at constant volume, then delta V equals 0. Cv equals delta Q by delta Tv equals delta U by delta Tv equals delta U by delta T. If delta Q is absorbed at constant pressure, we have Cp equals delta Q by delta Tp equals delta U by delta Tp equals P delta V by delta Tp. For a mole of ideal gas, we have Pv equals RT. This gives us P delta V by delta Tp equals R.